welcome back, and this is the big one. I am not going to stop filming until we get fully into the operating system. We are going to see that OS today, no matter what. In the previous episode, we got really close. We got the hawk drive all repaired, and it looks like it's trying to boot into the operating system, but we're hitting a roadblock somewhere. It's failing into this really tight loop that says ATTN print. And well, we gotta clear past that to finish loading the rest of the OS. And I've been talking with some people on the Discord, and we have a pretty good idea of what's going on. So let's hop over to the machine, take a look at what I think is going wrong. We'll make a couple of quick fixes and try booting it again. And I promise you we're gonna see an OS before the end of this video. So let's hop over there and get to work. All right, so the first step is to figure out what ATTN print is and where it's coming from. We know it's not coming from the bootstrap ROM because, well, we've disassembled the bootstrap ROM completely and there's nothing in there that even looks like it would be capable of printing ATTN print. But a couple episodes back, we managed to rip the entire removable platter off onto our hard drive. And then we were also able to figure out the directory listing and pull out the operating system alone. And well, we just ran that code through a disassembler that we have, and that made it a lot easier to search for the term ATTN print. It should be in there somewhere in ASCII. And sure enough, it is. This is the ATTN print subroutine, and well, we can see it just essentially prints the string ATTN print with a new line and a carriage return. But we do know from this code that it has to do with the multiplexer card, which means it has something to do with the connection between the MUX card and the terminal. Now, many episodes ago, we did some work on the multiplexer card trying to figure it out. I did just some really basic schematic work on it, and I also tried to figure out the pinout of what the DB25 that was connected up to the terminal was. And on pin 2, we have transmit, pin 3, we have receive, pin 5 is CTS, and pin 7 is ground. So we have 4 wires coming from the DB25 to the DE9 that's on the multiplexer card. Now, the multiplexer card itself is a bit more confusing. We have essentially 9 pins. 2 are tied to 5 volts through 2 resistors, 1 is tied to ground, and 1 more is tied to negative 12 volts. That leaves 5 pins that have to do with communication. Now, pin 6 is receive, pin 8 is transmit, and pin 2 is our CTS signal coming from the terminal. That leaves 2 unknown pins. We have pin 4, which is an output coming from a line driver, and pin 7, which is an input, which interestingly goes to a 74 LSO4 inverter. But what we think the problem is the multiplexer card is waiting for the CTS, the clear to send signal, to go high. But since there is not an RTS signal making it up to the terminal, the CTS signal sits perpetually low. So I think our solution here is going to be either to tie pin 2 CTS to VCC or connect pin 2 to pin 4. Because pin 4 is an output, that means there's a good chance that that is the RTS signal that's supposed to go up to the CRT. Now, this may not be a permanent solution, but it is one way that we can test it very quickly. A really quick and easy way to test this out is using this little RS-232 breakout tester. There's a female 9-pin on this side and a male 9-pin on this side. So it can just sit in between the MUX card and the cable going to the terminal. Now in the middle here, there's a 9-position dip switch, and this can either turn on or off the signals passing through. So right now, all of the switches are off, which means no signals will pass through at all. And we actually want 3 of our 4 signals to pass through. We want ground, which is on pin 1. We want receive, which is on pin 6, and transmit, which is on pin 8. But the CTS signal, which is on pin 2, won't pass through. And the terminal is going to be on the male side, and the mux is on the female side. So I want to jumper pin 2 to pin 4. And since I'm a bit of a nervous Nelly, I'm actually going to use a 1000 ohm current limiting resistor to do this, just in case. I'm still a little unsure of how well this is going to work. But it's ready to test out now. So we'll just unplug the mux cable here and slip our little breakout right in the middle. And now it's time to spin the whole thing up again. All right, we'll flip the main power on. That'll turn on the breakers for the hawk drive. The fans are spinning up. Turn the terminal on, turn the computer itself on. And then we will spin the hawk drive up. All right, the hawk drive has spun up. The heads are loaded. Let's, here goes nothing, H0. What? It did something. I saw LOS there. Oh, it's not gonna go down without a fight, huh? All right, so it says OS 7.1-E. We're in the operating system, and apparently it's version 7.1, but we've hit another roadblock. It says Parity Circuitry Inoperative. Oh man, so close, so close. All right, I think I have an idea where this is localized to, but I'm gonna need to talk to Ken and maybe a couple people on the Discord to get an idea. But I think we can overcome this pretty easily. All right, after talking with a couple of people on the Discord, notably Ken and Dave, I'm pretty sure that the problem is localized to our memory board here. And that makes sense because it said Parity Circuitry Inoperative. And well, if we look at the layout of the memory chips here, we have 8 columns for our 8 bits, and then we have 8 rows for the amount of memory we have. But the 9th row down here is a parity row. So if we have any parity problems, it's gonna be on this board. Now, I don't think that we have failing chips or anything like that. As a matter of fact, I think our problem is localized to these dip switches. Now, the 8 position dip switch down here is used for multiple memory cards. This is a 128K memory card, and the machine can support up to 256K. So we just kind of select the space that it lives in with this. And with the dip switches in the position that they currently are, this one says that it's in the space from 0 to 7. And so if we put the second 128K board in, it's going to be in the position from 8 to F. This dip switch up here, though, is very interesting because it allows you to essentially roll which column of memory it starts with first. So this is how they're helping you diagnose where you have a memory problem. But there's 8 columns, and this dip switch has 4 positions. We only really need 3 of these to roll the entire memory columns around. So this 4th switch is the big question mark. And talking with some people on the Discord, we're pretty sure that this is a parity control switch. So we're gonna go ahead and just flip that one up, then plug this card back in the machine and see if that makes a difference. All right, we've got our dip switch flipped. We've got the hawk drive spun back up. Here goes nothing, H0. Yeah, okay, it's getting to where it was before. We've got the cursor all the way over on the far right. I think we're in. OS 7.1-E, it says max disk number M equals 1, system disk S equals 0. Let's hit enter from here. Previous system date, 02/23/1988. So we'll just enter that same date, 02/23/88. Hit enter. Enter system time, we'll just do noon, 12:00:00. Hit enter again. It's doing something. I can see that the lights on the front are flashing. It's loading the operating system fully, hopefully. It says CRT0 ready. I think that's it. I think we're at the prompt of the operating system. Now, I've been talking to Ken, and I've written down a couple of commands to try here, so we'll just try to see the status of the computer, and that command is .sta. I'll hit enter. Yeah. All right, it says status display, revision 7.13, system date 02/23/88, total system RAM 256K. That's right, I put both memory cards in there just for fun to see what would happen, and we've got a full 256K of RAM in this machine. Below that, we can see the Hawk drive itself. We have two volumes. We have soft term and programs. And now, soft term volume 0 is the removable platter, and we can see that the date on it is, well, 02/23/88, the system date. But programs is the fixed platter, and it has a date of 9/13/1996. So this machine was used as late as 96, like late into 1996. We can see that I've got the 4-port mux in there, and it registered whatever's connected into port 0 as CRT 0. That's awesome. All right, so we know that we have the drives on here. Let's see if we can get a directory listing of the drive. So I'll do .dir space 0. We hit enter. Yeah, look at that. We filled up one page. I can hit space to go for more. And there we go. That is the directory listing for the removable platter. And we actually have a little script that we've been using off of the data that we pulled off of the platters on, the modern computer, the laptop, to view the directory listing, and they all match up. So if I do .dir space s dot space 0, this is going to show us the contents of the S folder on the removable platter. So if I hit enter, yeah, there we go. The S folder contains a lot of the applications. Most notably, well, the one I want to demonstrate today is KOMPOZ, KOMPOZ. It's kind of a play on words for composer. This, we believe, based on what we've been talking to with Ken and other people who used to work there, is the text editor that was part of the Centurion applications suite. And if we want to execute the composer, we'll type S dot and then KOMPOZ. We'll hit enter, and there it goes. It says text composition system compose, enter input file name. So we'll do TEST for test, hit enter, enter input library name or new line if no library, we'll just do new line. Enter disk number for the file test, we'll say disk number 0, we'll hit enter, and then it says file test not found on disk 0, do you wish to create? Now here's where we kind of hit a brick wall. If I hit yes, well, it's going to try and create the file, but it's going to give me an error of WP0. I'm still completely terrified of losing the data on the removable platter or the fixed platter, so I have the write protect for both turned on. So we're just kind of stuck here. So I'll hit Control-C to exit out of this, and it says abort 28 CRT 0 ready. Now it looks like I'm back at the prompt, but I don't think I am. We need to actually finish the compose system. It's still kind of running. We just aborted out of the write protect problem. So to close the program, we need to type .end. And then it gave us an error. It says use test on 0 at sys0 share. There's still a lot of stuff going on. So it says cancel, and then we'll just say yes. There it goes. Now it finally ended the program. Job canceled, job stream bypassed, .end, that's the .end that I was trying to run but didn't successfully run apparently. Now we're back up to the prompt. If I type .sta, I should get the status of the machine. Now when we ran the composer, we didn't actually run the composer executable. We actually just ran essentially a wrapper script. Now we're pretty sure that s.crt is a file viewer, But in between the cuts here, I tried using that file viewer on a file that's in a folder, and I can't seem to get it to work. So for example, if I do s.crt space s.kompoz and then tell it that that's on platter 0, and I tell it to go, it just says illegal parameter cancel. But I think if we use it on a file that isn't in a folder, we can make it work. So let's take a look at the directory listing for platter 0 again. So let's go s.crt space, and then we'll do rpascii. RPASCII. So RP ASCII. Tell it that that's on drive 0. Hit enter. Tell it that we don't have a library. And there we go. Now we're actually viewing the file RP ASCII on soft term. And this is a good example of the type of wrapper script that is used for how it's executing different types of software. So whenever we hit a period and we type a command after it, that's part of something that they're calling JCL, or Job Control Language. Now, I don't believe this has any relation to the JCL that IBM uses. I'm pretty sure it's its own custom thing. So we can see that .job is kind of setting up the job, and the job is this entire group of commands. And then we have .fspec, .skip, .delete, .use, and then .run. And .run xrpascii is the executable itself. So the X at the beginning of the file name denotes it as an executable file. But before we can run that executable, we have to essentially get all of our ducks in a row. And that's what the job is doing. Now, when the executable is finished, we do .end, and that cleans everything up, puts us right back at the prompt. That's how we think it's working at the moment. But you know, we could be completely wrong. But while we've got it running, let's take a look at a folder called question mark. So .dir question mark dot on drive 0 here. This folder contains all of the Centurion specific testing programs. We have TOS6, we're going to come back to that one in a bit, OS bug test, XC test, etc., etc. So let's just run one of these right quick. Let's go question mark dot test. Just a quick little test. There we go. Centurion test routines. And we start with number 1, the CRT test. And we have, well, I think the coolest one is going to be option number 1 here, ASCII barber pole pattern. So we'll hit number 1, hit enter, and yeah, that's very cool. Also, we can see what the max scroll rate is when you fill the screen full of text. It's not exactly fast. Now, there is one last thing that I want to show you guys, and that is TOS6. Now, TOS has been an unbelievable resource, but the TOS that we've been using should work on CPU 4, CPU 5, and CPU 6. But TOS 6 is special. But in order to get into TOS 6, we have to actually reboot and get to the Whipple prompt. So we'll hit the select button on the front. That'll get us back to D equals. We'll hit H0. It's going to load the Whipple, then load at load, and it puts us at the at load prompt. It says name equals. Now, I could get right back into the operating system by typing @OSN, but I actually want to take a look at TOS6. So I'll do question mark dot TOS6, hit enter. It says disk equals, that's going to be 0 for the removable platter. The code equals, this is right back to where we were, but it turns out there is no code. I can just hit enter. And there we go, 04F6, we're at the TOS prompt. Now, if I do M0100, I can look at whatever is stored at address 0100. This is exactly like the TOS that's on the diag board. But what we can do also with TOS6 is do D0100, 01FF, hit enter, and it gives me a list of all of the memory between 101FF. And you can make that as big or as small as you want. Not only that, we can view the individual registers in the CPU. So there is an A register, and we can set that to something else, like say 0000, hit enter, and now we've set the A register in the CPU to all zeros. There's also a B register, an X register, a Y register, a Z register, an S register, a C register, a P register, and there's also a V register, which I didn't know about until some of the guys that were reverse engineering the CPU6 told me about. Now, because this is TOS6 specifically set up for the CPU6 system, if we want to do anything with MMIO stuff, we have to add a 3 ahead of it. So if we remember, F144 and 145 are the status registers for the Hawk drive. So I need to do M3F144, and then I can view the status registers, which is 00B0, which, if we know from the previous episode, that means that our Hawk is working perfectly, which is obvious because we had the operating system. Now, if I want to get back to the operating system, I can do it 2 ways. I can hit the select button on the front. That takes me to the D equals prompt. From here, I can type H0. This gets me right back to the name equals. From here, I can type @OSN, tell it disk 0, hit enter, and it should boot into the operating system. However, if I push the load opsys button on the front, this will take me back to the D equals prompt, and if I type H0, it skips the name equals prompt and goes directly to loading up the operating system, which is what it's doing right now. OS 7.1, hit enter, previous state 022388, set the time to 120000, hit enter, and now it is loading the operating system up again, and it's going to take it a little second here, but it'll say CRT0 ready.sta, and there we go. We are right back into the operating system. It is all working perfectly. So what did I tell you? I said we'd get into the operating system today, and we did, and it is epic. Oh man, after almost 2 years of working on this thing, we finally did it. We got into the operating system, and it is everything I hoped it would be. But don't for a second think that we're done with this project. Most notably, we still have the Finch drive. And on the fixed platter of the Hawk drive, there is a little file called games that has about 5 or 6 games, but it all points to the Finch drive. So we have to get the Finch drive going to see what kind of games they had on the Centurion. But that means we have to get the FFC card repaired and talking successfully to the Finch drive. But above the drives, we have a bunch of other really cool stuff to dig into. Most notably, we have the line printer. I want to see that thing shooting paper out of the top. And now that we have a working system with a working text editor, although I have to get brave enough to turn these write protect switches off, I can get the printer card in, hooked up to the printer, and actually printing something out. But that printer's in very rough shape, and it's going to require a full restoration as well. Also, we have a complete another Centurion system to build. And I think using this Hawk drive as a working drive, we can actually repair the drive that we crashed. I can pull the crashed platter out, sacrifice one of our removable platters that just has boring accounting data on it, put that as the new fixed platter in that drive, clean it up, spin it up, and then copy the contents from the removable platter that has the operating system on it onto the fixed platter, and then we will have 2 fully functioning Hawk drives. So we still have a massive amount of really cool and fun things to do, but we hit a massive milestone today because we saw the operating system on this Hawk drive for the first time in what? Almost 40 years, 35 years or so. That is just epic. It's so cool. Such a long journey, but it was absolutely worth it. And I am so glad that all of you guys tagged along for it. And I hope that you guys tag along for all of the future projects that we have with this system. So I want to thank you all so much for watching and joining me on this journey. And I hope to see you in the next episode.